So we're going to talk about a number of other things that are going on. You know, we saw yesterday there's nearly 100 repositories in SymbiFlow. So there's a lot going on. So we're not trying to show you everything. We just wanted to give you a flavor. Like, for example, it would not have occurred to you that recreating a schematic from a bit stream was, yeah, that's an interesting project. Okay. So what are some other things that they have out there? Well, SymbiFlow is maturing to the point where they have a full tool flow. It's been working with a repository called Symbiflow-examples. And there are a number of Verilog designs here that you can go in and you can run a full-fledged tool chain, all open source, starting with Yosis through a SymbiFlow version of VPR, and then using prjxray, generate a bit stream and downloading designs to his board. He's taken his old 220 designs, converted them to Verilog, and it has been running a bunch of those. So, you know, this is one of the things they have put up. I asked Tim, you know, tell us what this is for. Is it to give a starting place for new people who come in to help them get going? Because one of the challenges with an open source project is the more people you get working on it, the faster it moves and the higher quality, et cetera, et cetera. So obviously you want to do things that will attract users. I said, is that what you're trying to do with this one? Or are you trying to come up with a repository of a bunch of test designs to test out your tool flow? And he said, oh no, it's the former. We want people to be using it, and you need sort of a launch pad. So that's what Symbiflow-examples is. And so if you go into it and look at it, it's just one of the SymbiFlow repos. They have Xilinx 7 series designs. They have EOS S3 device designs. And for each of those, they have full-blown tool flows that will synthesize, place, route, and bitstream generate for those. So for example, if you wanted to run some of your designs, you would just follow the example here in the SymbiFlow-examples. It has some installation instructions. It's like most things, you clone a repository, you maybe set an environment variable or two, and you type make, and it builds the needed environment. And from there, then you can go into their directories, you know, their sample directories. Let's see if I can find one. You're going to have to help me. Here we go, counter test. And here in counter test, there's a Verilog counter. There's an XDC file. If you're going to map it to the board that we're now using for 220, the base is 3, but here's an XDC for an ARTI, et cetera. And there's a make file, and if you type make, then if all goes well, it'll run the tool flow and you'll get a bit stream. So it is a complete replacement for the vendor tools at this point. They have a few examples here, okay? And so one of our students is going to add examples. He's going to document how to add your own designs to this flow, fix up the documentation, et cetera, and then go out and find other public, you know, open source Verilog designs and add them to this to start to build up a repository of things to help people get started. So that's one of the interesting ones. And so if any of you have interest and you wanted to tinker and be able to say, I have generated a fully working design using all open source tools, this is where you would start. You wouldn't go into the prjxray repository. That's just the bitstream database, okay? So that's one. Here's another one, which I mentioned the other day, prjxray-bram-patch. This is a BYU created repository. Jonathan Orgill did it as a part of his Immerse project 2 years ago, and then we worked on it all last year. But it basically takes a bit stream, it converts it to FASM using bits to FASM. It finds the initialization strings for the VRAM or the memory contents, and then it has tools that will go in and patch those initialization strings then do FASM to bits, and you now have a bit stream where when you configure that onto the board, the memory is initialized to different values. Imagine you have a microprocessor design and the program it runs is sitting in a bunch of VRAMs. This would be a way to easily patch those memories with the new memory image. Of course, the challenge here is you have a memory that your Verilog, your Verilog contains a memory and it's initialized using some Verilog commands, chapter 19 of your 220 text. And that file is formatted as, here's the word for location 0. Here's the word for location 1. When Vivado takes that design and synthesizes it in place and routes it, a large memory that you view as this nice linear array of values, it gets chopped up and spread across some arbitrary number of BRAM primitives on the chip. And so somebody's got to get all the toothpaste back in the tube to figure out, of all those 8 little BRAM blocks, where is this particular bit in that word? Where does it land in the design? And do all the conversions and translation so that it can put the bits where you want them, okay? The other thing is VRAMs in an FPGA, they are configurable. You can make it 32 kilobits deep by 1 bit wide. You can make it 1K words deep by 32 bits wide, okay? You can make it 512 by 64. I mean, there's a range, and I don't even remember all the variations, but it's a bunches of bits that can be configured to any shape memory you want, or at least there's a set number of sizes. And when they do that, they do odd things. And so the bits don't appear linearly in those initialization strings. They're all over. And so what Jonathan helped us do was figure out that mapping, and that's now embodied in a Python program. But you know, this is a nice little utility. So the hope is that things like this will grow and flourish within this SymbiFlow ecosystem. FASM is a key piece of that. Okay. Any questions about that? Well, I made a comment the other day where I said, we seem to spend half of our time creating file formats so that one tool's output can represent what it did. Other tools will consume that representation of the partially implemented design, do their step, and then they have to output something. And there have been a lot of these file formats over the years, and it seems to be a never-ending problem. One of the things to come out of SymbiFlow is something called the fpga-interchange format. They said, wouldn't it be nice if we had a nice, regularized, well-defined way of representing designs and FPGA devices? So to motivate this, I'm going to go back to a picture I showed you on Wednesday. Do you remember this? This was the RapidSmith. And RapidSmith, if you recall, the old Xilinx tools provided this XDL format that would allow you to take a design that had been partially implemented, pull it out in a textual readable format so that you could write your own CAD tools to do things with that representation. And then you could shove it back in and continue the process. There was a second file I never mentioned on Wednesday. There's a new box here. In addition to representing the design, it also had something that would represent what's inside the FPGA device. So now, by the way, before I talk about that, think about it. What does synthesis output? It outputs a net list. So if you pulled XDL out of the flow here, you would get the net list that Dr. Goders just talked about. Okay, and so forth. So XDLRC was a format that they created, and it's very verbose. I mean, 70, 80 gigabytes was not uncommon for the representation of an FPGA's contents. But it would say, here's this certain tile, here's his XY location, here's all the wires inside of the tile, here's all the sites inside of the tile. And so using that, you could recreate every wire, every programmable connection, every LUT, et cetera, et cetera. You don't know anything about their physical, how they're implemented, but it would tell you, and you could enumerate all the wires and pips and lookup tables and flip-flops and what have you in the entire design. So it was a map, and it was sufficient of a map that in RapidSmith, using it, that told us enough information that you could use RapidSmith to write a placement tool or a routing tool, because the XDL would tell you what the design was, but you had to know what were the resources available on the FPGA to map those design elements onto, okay? So they're two very different things, but you need both of them if you're going to have a CAD tool flow. Well, XDL, XDLRC only existed in a previous version of tools called ISE. When Vivado came out, it's been a decade now, hasn't it? Seems not that long ago. But when Vivado came out, XDLRC and XDL went away, and we were left without any kind of a format. And I had grad students who created ways of sort of accomplishing the same thing, okay, in and out of Vivado. But in the last year or two, something called the FPGA interchange format has come along, which I won't say it's equivalent to these, but it can serve the same purpose. That you can describe everything there is to know about the physical FPGA device in something that would serve the same role as XDLRC, and you could represent the design data, and that would take the place of XDL. To me, I've spent a decade wrestling with a lot of these problems with our CAD tool flows that we've been doing research with. So I get very excited when I look at the possibilities for interchange, because it will make a lot of the things we've done historically here much, much easier. Okay, so before we talk about the actual interchange format, how it works, I want to talk about something called serialization. Anybody know what it means to serialize something? So let's talk about how you might have done the equivalent in the past. And I will confess, I have written way too many programs about what I'm about to describe. You're writing some tools and they need to output something for something else to parse. And so you say, okay, well, I will create a text file format. You know, I'll output the tile name, space, site name, space, X coordinate, Y coordinate, blah, blah, blah. And you'll write a program that will walk through your data structure and output a textual representation, okay? And you know the format of the textual representation. Often you do this just to visualize your data structure, but you might use it to communicate that data structure to some other program. But of course, the other program has to read it. So you have to create a writer to write files with this new format that you dreamed up. And then in the other program that's going to consume it, you have to write a parser, okay? And if you've taken compiler classes in the CS department, you might say, oh yeah, I know how to do this. I can create a grammar, and there are parser generators, and I did a lot of that back in the 90s, okay? But the point is, yeah, somehow you got to write it, and then you got to read it. Well, that was the old dumb way of doing it, and I'm embarrassed to say that I did it for 25 years and it never dawned on me that there was a better way. Okay, so recently you may have heard about file formats like XML. Has everybody seen XML before? Okay, XML is a way of representing structured data. You'll have a tag that says, you know, maybe you'd have a tag that says design with angle brackets around it. And then you'd have a bunches of other information, and then you'd have angle brackets, you know, slash design, meaning here's the beginning of the design construct and here's the end. And inside you might have angle brackets surrounding things like port or name, okay, or wires. And it's a way of sort of structuring your data. It looks a lot like HTML in some ways, if you've seen HTML, okay? So that's a way of writing structured data. Now that's a readable format. What's the newer version that we use a lot now that we're all Python people. JSON is a very common format for that. We actually saw JSON files the other day, remember? Okay? And JSON has become very popular for writing structured data. And the reason it's nice is you do not, like with JSON, if you have a bunch of Python data structures, you don't have to think about the format it's going to be dumped to. Because JSON knows about dictionaries and it knows about lists, and that's usually what we use, right? Okay, so if you're just building data structures with lists and dictionaries, you can take this data structure and you can call JSON.write, and it will simply dump a JSON file of your data structure. And there's no parsing that has to be done. On the other end, you say JSON.read, okay? And all of a sudden, all that work we used to do to write all these stupid parsers, et cetera, is gone. Okay, so that's an improvement. Would you all agree? Okay. However, JSON is text, and it's pretty verbose, right? Okay, and it's also, you know, when you get a nice formatted JSON file, it's spread out so much you don't see very much on the screen, so it's not terribly compact. But the main problem is it's text. That is a plus, but it's a minus in that it would be big. Okay. And so people have created other ways of taking data structures in your program and dumping them to disk in a way that it's easy to dump them and it's easy to pull them back in. You don't need to spend 10 minutes parsing this file. If you can dump it in a binary format that corresponds to the data structure, then you might be able to suck it back in very little time. We call that serialization. And so rather than define file formats to save the data that your program has computed, depending on how you're going to use it, you might simply serialize the data structure directly to disk in a binary form. Now, when I first saw it, we were doing serialization back in RapidSmith days of Java data structures. And so there was a serialization package, and it would serialize it out, and then later we would read it back in. And it worked really well. And we used it for lots of things. Well, other languages have their own ways of doing it. Anybody ever heard of Pickle? This is a Python object serialization. So notice, I'll just read you a little bit. The Pickle module implements binary protocols for serializing and deserializing a Python object structure. Okay. Pickling is the process whereby a Python object, there's that better, is converted into a byte stream, and unpickling is the inverse. Because if you have a byte array, it's pretty easy to write that to disk. It's very efficient, right? You do a low-level write of this many bytes out to that file and close the file and you're done. And so the pickling, unpickling takes that and does whatever is needed to turn it back into your data structures. But the point is, you don't have to worry about that. It does it automatically. Okay? So Python has its own mechanism. Well, someone else came along and said, we want to do it slightly different. So Captain Proto, okay? And notice they call it a serialization protocol. So I guess the Captain Proto is the takeoff on Captain Crunch.
Right? Spelt it like cereal, like breakfast cereal.
Yeah, because Captain Crunch is our favorite breakfast cereal, right? See? So whoever did this has a bit of a sense of humor. So this is an interchange format way of doing things, but it's a little different than Python pickling in that well, actually, I will not say I understand all the differences, but Captain Proto has always been represented in the things I've read is the beauty of it is it's independent of the language you use. You can serialize your data structure from Java, and you can deserialize it into a Python program, which means that there's some standardized ways of serializing the various data structure elements. And so it makes it an interchange format between any programming language you want, okay? And if a new programming language was invented, someone would just have to create a library to go in and out of it. So you might want to look up Captain Proto if you're thinking about ways of communicating data between programs and you don't want to worry about how to write it out, but it needs to be compact, this is a great way to go. Okay, everybody with me so far? So we've been talking about serialization for a while. So the big idea was, let's create an interchange format to describe FPGA designs. So we don't have to be writing and reading netlists. We'll just serialize a Cap'n Proto description of the netlist, okay? No parsing involved. But we're also going to serialize descriptions of FPGA devices, the tiles, the sites, the wires, the pips, et cetera, et cetera. And so what was created was something called the Symbiflow-interchange, okay? Now, there's a couple of projects I'm going to show you. These are all inside Symbiflow. This work has actually been done, I believe, in conjunction with Xilinx, because this ties into a tool that Xilinx has that we haven't told you about. I'm going to give you 30 seconds. Chris Lavin, who did RapidSmith here when he was a PhD student that I worked with, he's now at Xilinx, and he has created a new tool called RapidWrite. That's write with a W-R-I-G-H-T. The idea was RapidSmith was sort of a blacksmith theme, and it was an anvil and a hammer was our icon. Well, in keeping with the same idea. It's a toolbox. It's a way of creating CAD tools, okay? So RapidWrite is like RapidSmith in that it provides a mechanism to get in and out of Vivado, okay? And so it can hide all the Vivado data structures so they don't divulge what's going on, but it provides an API. So you can use it's a Java package, but you can write Java programs and you can query the device representation. Give me a list of all the tiles. For this tile, tell me what sites are in it. Where's this cell mapped to, okay? How's this wire hooked up to this and that? But as a part of RapidWrite, Chris has created the ability to read and write this FPGA interchange schema. So you can take a design in Vivado and you can fire up RapidWrite and it will take the design out of a Vivado checkpoint and it can serialize it into this interchange format, which means we now have a way to get in and out of Vivado. But because the interchange format is a standalone format with its own schema, any other tools can read and write it. And so the hope is that it becomes the hub for FPGA tool ecosystems, right? If you're going to write placers and routers, why don't you just use the interchange schema to read and write what you need? Because it's, like I said, it supports design data. It also supports device data. Okay? So with Cap'n Proto, you define the structure of how the data is going to be stored on disk using something called a schema. And a schema is basically just sort of the grammar. And I thought I would show you some. So there's a project called FPGA Interchange Schema. And in the interchange directory, there's 4 schemas. We'll look at the logical netlist schema, okay? Since we've talked about logical netlists here a minute ago. So if you look at it, it almost, look, it uses the word struct. And in some ways, it looks like struct or class definitions, or at least you look at them for a few minutes and you go, oh, I get it, right? So it says, well, look, I have something called a netlist. And what are the members of the netlist? Well, it has a name and it's going to be a text element. And then it has something called a property map, okay? But the property map is defined as its own struct later in the file. Okay. It also has a string list. That's a list of all the names of things inside the net list. And it has the list of ports and cells and who's the top level instance, et cetera, et cetera. And then if you were to go down and say, well, what's a property map? Let's just search for property map. Okay. And we'll go find the definition. Okay, what's a property map? Well, a property map is a struct, okay? And it has a list of entries, okay? Well, what's an entry? Well, an entry has a key and a blah, 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 okay? A string index and a string ref, and it Down here it has a union. So it looks very C-like in some ways, but it's defining the structure of the data. And so you take your data structure and you say, I want this data structure to go into this schema and into a cat and proto file. And it's like 2 subroutine calls to do that. And then on the other end, you do the same thing. You say, this is the schema I'm using. There's the file. Go get the data and put it into data structures for me. Okay? And so they've defined one for net lists. They've defined one for devices. So this is the equivalent of that old XDLRC, sort of. Okay? I think it's superior for many, many reasons. But as you can see, you've got the device has a name and a list of strings and a list of site types and so forth and so forth. And so if you were to go into, for example, Rapid Write, you can dump a detailed description of your FPGA device with all the wires, tiles, sites, everything. And then using the schema, you could write a program that would load that into a data structure and do whatever you want with it. So we now have this ability to write CAD tools using this new interchange representation, okay? Now, reading the schema and figuring out how to interpret what comes out of the file takes some work. And so what would be the logical thing to do? Write a library that provides a layer of API calls to make it easy to get at the stuff stored in the cat and proto representation, right? Okay. And so there's another project in SymbiFlow called the python-fpga-interchange project. Now it contains a lot of things for reading and writing BLIF files and who knows what, but one of the things it does is it can read and write the FPGA interchange. And so if you use this package, you can write a Python program, and in just a couple of lines, you can say, this is my schema, that's the file, read that in, and what you get is a big set of Python data structures with a bunch of API calls to make it easy to query the data structure to figure out what you want to figure out about the net list, if it's a net list you've read in, or the device representation, if it's the device representation you've read in. And so we have some project where students are using this FPGA interchange format with the Python layer on top. And we're using this for things. And like I say, I'm excited. I'm hoping it will go places because I think it will enable lots of work in the future. Of course, what's the first thing I had a student do? I said, we've had this XDLRC and we've got lots of old software that works with XDLRC files. Can you read the interchange format and output an XDLRC file? And so I've had a student working on it, an undergrad, for the last couple months, and he's about done. And the answer is, yeah, you can. Interchange contains more information than the old XDL and XDLRC did. So anyway, so those are some things that are going on. Now, there's one last thing, since we have a minute or two, I want to talk about, and that is, if you recall, we mentioned a project called Verilog-to-routing, okay? Now, Verilog-to-routing is not a SymbiFlow project. It actually is run out of University of Toronto, okay? And as I said last time, Dr. Goders was actually involved in that as a master's student. And it has a full-blown CAD flow. It has a synthesis tool, it has place and route tools, but it doesn't have bitstream generation. And one of the things that's going on is if you go to SymbiFlow, and I will do that right now, there is a repository here inside SymbiFlow. So SymbiFlow has their own version of VTR. It's a fork. And what they're doing is they're working on, let's take all the information that prjxray is gleaning about the devices, and let's create device representations so that VTR could be used to target a 7 series Xilinx part. Okay, and so that's what this SymbiFlow VTR Verilog-to-routing is doing. And so if you go clear back to where we started, if you were to go into Symbiflow-examples and run some designs through, you're running the SymbiFlow version of VTR using the prjxray generated databases, okay, to do the whole place and route part, okay? And so there's that piece of the puzzle. So all these open source things are, you know, they're intersecting in very positive ways. So that's what did I miss, guys? Faculty here. Hopefully that's
There's a lot behind this. This is like a touching, a really high level overview, but there's a lot.
High level overview, yeah. Now the reason we've given you this high level overview is that the person who's going to talk on Monday here is a key person in SymbiFlow. I don't know if he's the boss, if there is a boss, but he's the person that we view in that role, right?
I've never heard of his boss's name, so I don't know.
Yeah. So he's basically the SymbiFlow guy in terms of, you know, knowing what's going on and making a lot of the key decisions. And so we wanted you to have a feel for what this prjxray and then the bigger umbrella is all about. So he doesn't have to spend an hour doing what we've just done. He can talk about other things, okay? And he'll be able to answer questions. We don't know what he's going to talk about, do we?
No, but we don't often get like Google developers coming to talk to us at BYU. So
he's a very high power developer who's very involved in this project, as well as many other things. Every time I turn around, I see his name associated with other open source hardware things. So very capable. And so he's become a good friend of our group here. And so we're excited to have him come. So hopefully you have a frame of reference. The thing you could do to get more out of his talk than anything might be to wander through SymbiFlow and look through and just see what kind of, what are those 93 repos or whatever it is, the repositories inside the SymbiFlow organization. Now you're aware that when you're at a project in GitHub, you know, you click this and you get to that project. But if you click the left half of the name, you get what's called the SymbiFlow organization. And an organization can have repositories or projects under it. And so SymbiFlow is the organization. And you remember, it's 73. There's 73 repositories in here, all right? We have a BYU CCL organization. I have no idea how many repositories we have. Do you know?
over 80.
We have 80. Oh my word, we have more than them. Well, when you got, you know, we're using it for all kinds of things, right? We also have a BYU CPE organization. You know, that's where the boot camp stuff is all hosted. So anyway, if you have some time, the way to get the most out of his talk might be to wander through and just see what you can see what you can learn, okay? It might be an interesting way to learn what is all this other stuff that GitHub is giving you, right? You will see our students' names in various and sundry places. You know, if you look here, oops, it was there just a minute ago. No, it wasn't.
You can always go to the repo and see the little pictures on the right. Just scroll down, contributors. So.
Yeah, there you go, contributors. For example, Ryan Johnson, his name is spread throughout there because he's making pull requests, he's making contributions. So has your first pull request gone through, Josh?
Not yet.
Not yet. Okay, so he's trying to get his first one through on Symbiflow-examples. In fact, we can see his pull request, right? Which one is it?
First one, a few minor clarifications.
Here we go. So this is our own White Ninja Z, also known as Joshua 5, okay? And so some of you are already doing this and some of you may get involved in the future, okay? So please be here on Monday on time. We're going to start on time. I would ask that you sit in the first 2 rows. Now, he's remote, but if you want to ask questions, you don't pick up. Anything beyond like the second or third row doesn't pick up with the overhead microphones. And so I've noticed as I've been watching some of the videos we're making and you can't hear anything that the students say. So in fact, if people have questions, we may ask you to walk up front to make sure that it gets picked up.
Where that's it.
It's right there.
That's that cross thing, yeah.
And it's got all these TVs right in the way, so I think that.
No.
Yeah, I think that's part of the problem, yeah.
It's really
So-
fancy.
So the hope is that, you know, but I would like, if questions get asked, I'd like them to, you know, show up on the audio. I hope he lets us post his talk. I have no idea. So, okay, if there are no more questions, that's it for today. Oh, I have one more thing to say. There are some activities for Project X-Ray and other things, but we're kind of in that part of the course where if your faculty advisor thinks it's important, they'll tell you, yeah, you probably ought to work through that one. Okay, we're sort of past the mode of we want everybody to be working through all the activities. Okay. And we're actually going to be done lecturing here in about a week. So we're pretty much done. Okay.